Being surprised by something, like, a surprise party or a surprise get-together or a surprise gift, it's wonderful. And other times, surprises are not so good. For example, if we're in the middle of a certification exam and we see some content or some topics that are not listed on the blueprint, the exam topics, that's not the best way to be surprised. So in this video, I'd like to help you solve that problem regarding a routing protocol in the world of Cisco. And to emphasize this point, let's talk about a problem that every router has on the network. And that is, oh no, what do? I just got a packet. How in the heck do I forward this packet in the right direction so this packet can get, like, from Bob, the user, over to the server that Bob's trying to reach? So let's imagine that Bob is over here and the server that Bob is trying to reach is over here. And this server is on the 10.4.0 network with a 24-bit mask, and perhaps its IP address is like .10 or something like that. So if Bob, being the client that he is going to use his default gateway, which would be this interface here on R1, when he gets a packet destined for 10.4.0.10, that router needs to know, okay, what do I do with this? How do I forward it? Now, one solution to this is to use a routing protocol. So if we consider these networks like streets, so those are street names, and we consider a routing protocol, that would mean that each of these routers that are connected to streets would be willing to talk to their adjacent router. So R4 could tell information about this network, this street, 10.4. It could tell it to R3, and then R3 could tell that information to R2, and R2 could tell that information to R1. And that's the basic idea of a routing protocol, allowing these routers to communicate amongst themselves to educate the routers on, hey, if I do get a packet for this street or that network, how do I forward it? And by using a dynamic routing protocol, these routers can automatically share that information with each other. Now, although there are lots of different routing protocols, the routing protocol I'd like to chat with you about in this video is called EIGRP, the Enhanced Interior Gateway Routing Protocol. It's like, give me an E, give me an I, give me a G, give me an R. So EIGRP has been around for a long time, and it is not, I repeat, it is not listed on the blueprint for the CCNA, but am I hearing a lot of people saying, boy, I wish I'd known a little bit more about EIGRP before I went in for the certification? The answer to that question is yes. So with that in mind, let's take a closer peek at how EIGRP, this routing protocol that shares information between routers about how to reach networks, let's take a closer look at how it works. So to do that, let's focus on this street name, which in IP networking, we call it a network address, this 10.4.0 network, which represents this group of devices over here, or this street of network devices. And if we're running a dynamic routing protocol, we have some options. We could use RIP, which is a dynamic routing protocol, letting them talk to each other. We could use EIGRP. We could use OSPF, and they each behave a little bit differently, but we're going to focus on EIGRP. So let's imagine that we have enabled, sort of like an app on a phone. You turn on the app and you enable it, boom, it starts working. Well, and imagine we enabled EIGRP, this routing protocol, on each of these routers, and they start talking to each other. So the question is, what are they saying to each other? So with EIGRP, there's a lot of information that R4 regarding this network that it's going to share with R3. But I want to share with you the most important aspects of what information it's going to share regarding the street with R3. And it boils down to this. R4 is going to tell R3, hey, dear Mr. R3, there's this network, 10.4.0.0 with a 24-bit mask. Come join me for Subnet Saturdays if you don't understand IP addressing yet, and we'll get you all sorted out. Now, as R4 communicates over to R3 and says, hey, I know about this network, this street, 10.4.0, it's also going to share with R3 something called the delay. Now, a delay is associated with an interface by default. So if this interface is a gigabit interface, the delay is 10 microseconds. Now, a microsecond is one millionth of a second. So R4 says, hey, I know about this network, 10.4.0, and the delay is 10 microseconds. He's directly connected to it on this interface right here. So he says, here's the network, here's the delay of 10 microseconds. The other thing that's critical that R4 is going to communicate over to R3 as we talk about this street, this network, besides the delay, is the bandwidth on that interface. So if this interface is a gigabit interface, that information regarding the bandwidth would be communicated as part of the EIGRP routing information for that network. So a gigabit is 1 million kilobits per second. So let's do a quick recap. R4 is advertising the 10.4 network over to R3, and it's including two basic pieces of information. Well, actually, a lot more than that, but two that are important. And those two elements are the delay and also the bandwidth associated with that network. Now you might say, well, Keith, bandwidth and delay, how do we verify that? That's a great question. Let's take a closer look at how R4 knows about the bandwidth and delay for that network of 10.4 that it's advertising. So if we go to Packet Tracer, and you might be saying, oh no, Keith, are we going to have a Packet Tracer lab associated with this? The answer is, yes, we are. So I'll make this available. There's going to be a link below where you can just click on the link, download this Packet Tracer lab. I'm using version 7.31 for this version of the Packet Tracer lab. So you can do this hands-on right alongside with me if you would like. So here on R4, if we go to R4 and we do a show IP interface brief, I just want to verify we have the correct interfaces involved. So this interface right here, Gigabit Ethernet 0/1, is directly connected to the 10.4.0 network. And if we do this command, show interface gig 0/1 and press enter, oh, no, too much data. Well, there's a lot of output here from this command, which is show interface gig 0/1, but the critical pieces we need are right here. And this is specifying that the bandwidth associated with that interface, where that network lives, is 1, and I'll just highlight 3 zeros here, is 1 million kilobits per second, meaning it's 1 gigabit. And the delay associated with that interface, says this router, is 10 microseconds. And a microsecond is 1/1,000,000th of a second. So that's 10 of them right here associated with that network. So what should happen as R4 is advertising the 10.4 network over to R3, it should be including the bandwidth associated with that network and also the delay. So we should expect to see a 1 million kilobits per second regarding bandwidth and a delay of 10 microseconds. And I thought to myself, oh man, it would be so darn cool to do a packet capture like with Wireshark or something like that and actually show that advertisement from R4 to R3 that includes those two important factors of the delay and also the bandwidth. And I thought to myself, you know what? Let's do it. And here it is. This is an update being sent from R4 over to R3. And if we take a look at the payload, so at layer 3, here's the layer 3 header. It's pointing to the layer 4 protocol of 88, which is a layer 4 protocol for EIGRP. And then if we expand EIGRP and take a look at it, here we have that route, that 10.4.0 network that's being advertised. If we expand it, we can take a closer look at what's in the details regarding that network that R4 is advertising to R3. So if we scroll down a little bit and expand the wide metric section here, there's a lot of details here, but here are the points that are really important. And that is the bandwidth. So that bandwidth is 1 million in kilobits per second, which is 1 gigabit. And here's the delay, which is 10 million, representing 10 microseconds. So good news. We're advertising that literally from R4 to R3 regarding that 10.4 route. Now, how do we verify, or what do we do with that information on R3 once we learn about it? Now, in EIGRP, the two major factors that routers are going to use as they calculate the metric. Now, in OSPF, it'd be cost. For RIP, it'd be the hop counts. In EIGRP, we call it a composite metric. And the way that this metric is calculated regarding any given route, it's going to take the worst bandwidth in the path and a sum of the delays. So if R4 just advertised that the bandwidth is 1 gigabit, and this is also 1 gigabit, R3 says, great, I'll just keep using the value of 1 gigabit in my calculations. But because my own interface, says R3, has a delay of 10 microseconds, I'm going to go ahead and take the advertised delay of 10 microseconds that you sent, add that to my 10 microseconds for my own interface, and the result would be 20 microseconds. So the secret here is for the composite metric, it's a combination of the worst bandwidth in the path and the sum of the delays. So worst bandwidth in the past, sum of the delays. So if R4 advertised a delay of 10 microseconds and our own interface is 10 microseconds, which we'll verify here in a moment, R3 is going to consider the delay, the sum of the delays up to this point, to be 20 microseconds. The 10 that R4 offered or advertised, and the R3's 0/1 interface that has its own 10 microsecond delay. So we can verify that here in Packet Tracer, and we can go to R3. And here on R3, we can just do a show IP route. So here's the route for 10.4.0. It was learned via EIGRP. That's the D there on the left-hand side. And if we do a show IP route, and we plug in that network, and I'll just copy and paste it here. Copy that, right-click, copy, and paste. and press enter, it'll give us the details regarding just that route. Check it out. It's saying the total delay is now 20 microseconds. Well, why is that? Well, it's because R4 said the delay is 10 microseconds from my perspective, and R3 said, well, my interface has a 10 microsecond delay as well on my gig 0/1, so I'm going to add that to it as part of the calculation. And we could verify that with a show interface gig 0/1. And let me show you where that is in the topology. That's this interface right here that R3 is learning the route on. And that's what we're going to look at right now. So here's a show interface gig 0/1. And I'm going to just do a pipe symbol and say include any lines that have a capital BW in it. And that will show us just that one line of output that we're focusing on. So here it's showing that the bandwidth is still 1 million kilobits per second because everybody to this point is using gigabit Ethernet. But check this out. My interface delay on gig 0/1 is 10. And that's why we got an advertised of 10 microseconds and we have our own 10. And that's why for our EIGRP composite metric, we're using now the factors of the minimum bandwidth in the path, which is 1 gigabit per second. And now on router 3, the microsecond total of 20 microseconds. So let's discuss a few things. On this interface right here, which is directly connected to the 10.4 network, it's a gigabit and the default delay is 10 microseconds. On this interface, where we're learning the route, it's also a gigabit interface, and by default, it has a delay of 10 microseconds. And the same thing is going to be true for here and here. So if each interface, as that route gets propagated, so R4 tells R3, R3 advertises it over here with a sum of the delays of 20, and R2 is going to add 10 more. It should be 30 here. And if R2 advertises a delay of 30 over to R1, R1 should see a delay of 40. So to verify that, and you can do this in the Packet Tracer Lab as well, let's go to R1. We'll take a look at the details for 10.4.0, and let's just verify that he believes that the sum of all the delays up to him, right here at R1, the sum is 40. And that would be 10 here, 10 more here, 10 more here, for a total of 40, with R1's delay being added. So here in R1, let's do a show interface gig 0/1, just to verify that his delay by default is 10 microseconds. There it is right there. And then let's do a show IP route. So he's got the route to 10.4.0. It was learned via EIGRP. There's the composite metric right there. And to create that composite metric, R1 took the advertised information, including the delays up to that point that R2 had, and also the worst bandwidth in the path, and then calculated this composite metric on his own router. So here on R1, if we do a show IP route, and we just put in that specific route by copying it and pasting it in, it'll give us additional details regarding that specific route. And check it out, look at this, 40 microseconds. So there is the metric that it calculated. We also call that the feasible distance in the world of EIGRP. And there is the minimum bandwidth in the path of 1 million kilobits per second, which is 1 gigabit. And it used this sum of the delays and the minimum bandwidth in the path to calculate that final composite metric. Now, you might be thinking, you know what? I'd like to get my hands on that Packet Tracer Lab and give this a go and verify all that. Great. I encourage you to do it. I'll put the link in the description. Just download it and have at it. Again, it's Packet Tracer version 7.3.1 that I'm using for this demonstration. Now, how would we tweak it or modify it? In reality, we could modify either the bandwidth on any of those interfaces, any of those gig 0/1 interfaces, or the delay on any of those gig 0/1 interfaces, and that would modify the downstream router's opinion and metric calculation for those routes. So let's go ahead and devise a plan on what to tweak and modify. I'll demo it, and then, my friends, I want you to do it in the Packet Tracer Lab. So let's do this as a tweak. If we took R3's gig 0/1 interface, which has a default delay of 10 microseconds, and we made it 110 instead of 10, that means the metric over here on R1 should go from 40 to 140 if we're going to increase it by 100. That's also going to affect on R1 the ending final metric that it uses, because it's using the sum of the delays. It's also using the lowest bandwidth in the path. So on R3 gig 0/1, let's modify artificially the delay to make it look like 110 microseconds instead of its default of 10. So here in Packet Tracer, let's hop over to R3, and we're going to modify this interface gig 0/1 and increase its delay. So here on R3, we'll go into interface configuration mode for gig 0/1, and we will specify a delay of, now it wants this delay in tens of microseconds. So if we said 11 times 10, that would be 110 microseconds. Let's go ahead and specify that. It automatically bounced the neighborship for us, which may or may not happen on live gear, but that's okay. And then we'll do a do show interface gigabit Ethernet 0/1, and I'm going to say pipe include BW so we can go ahead and take a look. Look at that right there. So I just wanted to verify that the delay truly had been changed to 110. So because we just bumped up on R3 on this gig 0/1 interface, the delay from 10 to 110, the result over here on R1 of the sum of the delays should be now 140 instead of 40, because we increased it 100 over here on R3, it should increase by 100 over here as part of the sum total of all the delays over here on R1. Let's verify that. So we'll make a road trip over here to R1, and on R1, where it was 40 microseconds just a few moments ago, we'll just use the same command, show IP route, and boom, check it out, it is now 140 microseconds. Also, notice that the metric increased from, it was 3584 and now it's 6144 because it's taking into consideration the sum of the delays across the network as part of the composite metric. The other thing we can do while we're here, we got the lab open, let's do it, is right now it's looking at the worst bandwidth in the path. And currently everybody's gigabit Ethernet, so that's the worst bandwidth. However, we could tweak that too. So the way the worst bandwidth works is, if there's ever bad news, like if R3 says, oh no, I've got a 64K connection, really slow, it's going to advertise that as the worst possible bandwidth in the path between itself and the destination network. And R2 would say, oh no, 64K, I'll pass that along. It's like, you know, gossip and rumors, passing on the worst possible information as far as, you know, the situation. So once we have a lower bandwidth, all the other routers that are advertising that are going to propagate that lower information. So let's do that. Let's go here on R3 and we'll modify gig 0/1 that instead of using the default bandwidth, which is 1 gigabit per second or 1,000,000 kilobits per second, that we wanted to use something really bad, like 64K. So back in Packet Tracer, we'll go back to R3 and we're going to tweak this interface right here, gig 0/1, and specify that we want to tell it that the bandwidth on that interface is no longer 1,000,000 kilobits per second or 1 gig, but rather 64K, making it really bad. And then what R3 will do, he'll pass on that information like, oh, here's the worst bandwidth in the path. And then R2 will pass that on to R1. Here's the worst bandwidth in the path. So that each of the downstream routers are going to use that worst bandwidth in the path as part of their composite metric calculation. And one of the elements I'd like to share with you is that when a router like R4 is sharing information with R3, and R3 is sharing it with R2, and R2 with R1, that information regarding the worst bandwidth in the path and the sum of the delays up to that point, that information is referred to as the advertised distance, not to be confused with administrative distance, but the advertised distance in EIGRP, also sometimes referred to as the reported distance, is the information, among other things, about the worst bandwidth in the path, and from that perspective, from that router who's advertising, the sum of the delays from itself all the way to the destination network. All right, so here on R3, let's make sure we're in the right interface, gig 0/1. Let's do a bandwidth statement, and we'll specify that we are going to do 64. I mean, going from 1,000,000 kilobits per second to 64, talk about bad news. So what we also could do, if you want to force this, you could also do a shut of that interface, wait a second, no shut, make sure everything converges. But right now what's happening is that bandwidth of 64 is being advertised as part of the information over to R2, and R2 is going to continue to propagate that information about the worst bandwidth in the path over to R1. In fact, you know what I'd like to do? Let me show you a packet capture right here between R2 and R1 that shows that R2 is literally advertising that information about the worst bandwidth in the path, and now that should show up as 64 kilobits per second. And that's because R3 is reporting that as the worst path, and R2 just propagates that information regarding the worst path, and then R1 will use the 140 microseconds and the 64K in the calculation for its composite metric regarding the reachability of 10.4.0. All right, so this was captured between R2 and R1. And so if we look at the payload in the EIGRP payload of this packet, which is an update, a routing update, here's the network 10.4.0 that's being advertised. We can expand that and scroll down. I'll expand this part that's going to give us the details regarding the worst bandwidth in the path, as well as a sum of delays up to that point. And so here's the delays. And so what's happening is R2 is advertising from its perspective that the delay is 130 microseconds, and it's advertising that over to R1. It's also advertising here that, bad news, the worst bandwidth in the path is 64K. So take that, Mr. R1, and use that as part of your calculation for the metric going forward. And we can verify that by going over to R1 and taking a look at the details of that route to verify that he believes that the worst bandwidth in the path is 64 and that the delay is 130 microseconds plus his own interface 10 microseconds, which should be a total of 140 that we looked at just a few minutes ago. So we'll go over to R1, and here in R1, this is the routing information for that network just a moment ago, 140 microseconds and 1 gigabit per second. We'll hit the up arrow key, press enter, and now it's showing the delay of 140 again because that didn't change from our last time. But check this out. Instead of having a gigabit or 1 million kilobits per second, it's now using the value of 64K as the worst link in the path to get to that network. And check this out. The metric that it calculated previously was 6,144, and now it's like, what is that, 40 million? Yeah, 40 million and change. And that's because the minimum bandwidth in the path is just so terribly low that it makes it a really, really terrible, compared to the previous metric, a much worse metric. But, you know, at the end of the day, if you do a show IP route, you're going to take the best path that you have. And so there's our current route for the 10.4 network with that really, really wacky, big metric. All right, so now you know the truth about EIGRP and the composite metric. And here's what I would challenge you to do. I would have you not just watch this video and say, oh, that's interesting, especially if you're pursuing a CCNA or a CCNP, because understanding EIGRP is important for both of those certifications, even though it's not explicitly listed in the blueprint items on the CCNA exam. So to help reinforce this, go ahead, download the Packet Tracer Lab. I'm using version 7.3.1 or newer would work as well. The link for that free download is in the description of this video. I'd like to have you download it, take a look at it, walk through this video again, and use the Packet Tracer Lab to go through it step by step. You'll get a better understanding of EIGRP if you do. Also, every Sunday, I think we have like, I don't know, dozens of them. We have quizzes every Sunday regarding Cisco topics, normally at the CCNA level. And one of those quizzes is all about EIGRP. So if you're asking yourself, do I understand it well enough? Should I learn it more? I would have you, I'll put a link for that as well, for the online quizzes. Just find the one on EIGRP, take a few minutes, go through it, have some fun. And if you are not comfortable with any of those questions as far as EIGRP goes in the quiz, I would encourage you to dig a little bit deeper. If you need support on EIGRP or you want to have a chat with me or other people on the Discord server, that's also free. The link is in the description below. We would love to elaborate and talk about EIGRP to make sure you are comfortable with it. So to reinforce what I said at the beginning of the video, surprises can be wonderful. However, if it's a surprise topic that you were not expecting in a certification exam, not so wonderful. So now you've been warned. I've given you some tools to better understand EIGRP, and I wish you, my friend, the best of success.